And I'll turn on the other one just in case. I have two methods of recording, so that in case one messes up, I have a backup. Alrighty. All right, so what do we have so far? We have the definition of a joule. We have the relationships, joules and calories. We have um, delta E, which is Q plus W. And just go ahead and write that down here. Delta E, which is the heat plus the work. All right, let me clean up this delta a little bit. Here we go. All right, now, the only thing that's really interesting about delta E is that you have to be able to decipher a word problem and decide, really, is it positive or is it negative in relationship to the system, and add them up. That's all you have to do. Okay. Now, it takes a little bit of practice to deal with the verbiage in the word problems. It's not a very big deal. Now, and here's the thing, and is that after all that trouble in chemistry, no one ever uses delta E, but we still have to be able to do it. We have to be able to take, the heat from a problem, the work from a problem, and we have to be able to figure out what the sign is. Okay, no one ever uses delta E. What we do use is something called delta H is what we actually use. And this is called enthalpy. It's called enthalpy. All right. And delta H means a change in the energy, but it is assuming constant pressure. Now, when we did delta E, we were doing pressure volume work. And so the volumes or the pressures could change. And so we end up with a work term and doing some, and if we assume constant pressure with some manipulation, we end up with something called delta H, which we call enthalpy, and delta H equals Q. In other words, there's no W term, no work term. Now you may say to yourself, well, why does that matter? Well, let me tell you, heat, the flow of heat is very easy to measure. All you need is a thermometer, because that's what thermometers do. They measure changes in temperature, and changes in temperatures is related to heat flow. Work, on the other hand, is very hard to calculate. Work can be calculated, but it's not a very easy thing to calculate. All right. And you may say to yourself, well, shoot, there is work. There's always work. There's always work being done. Look, when you're doing a reaction in a laboratory and it's open to the air, guess what? It's a constant pressure reaction. When you take two solutions and you just mix them together and you see what happens, it's a constant pressure reaction, which means there's no work term. It means that it's very easy to calculate because all you need is a thermometer and you can see the temperature change. This is very easy to do. And it actually turns out that even if you do a reaction at something that's not constant pressure, let's say in a sealed container where the pressure can change, it turns out the correction is usually so small that no one cares anyway. So by doing this, by having something called delta H, or the enthalpy, we actually simplify and make our lives a whole lot easier. And so if you look in the back of the textbook, you'll see selected thermodynamic quantities, and you will not see a delta E in the bunch. That's because nobody uses delta E. Everybody uses delta H. And if you have to do some sort of correction for pressure changes, then you do. But generally, 99.9999% of the time, we never care. All right. So we have something called delta H, or enthalpy is what we have. Okay. Now, before I go into the whole what we can do with enthalpy is first off, I want to put up here something called the first law of thermodynamics. The first law of thermodynamics. There's actually several, but we're just going to do the first one. First law of thermodynamics. And there are several different ways of stating the first law of thermodynamics. And we've actually been using the first law of thermodynamics for the last hour, really. Because when I said, well, the energy is lost by the surroundings, well, it's the same as the energy gained by the system or whatever. And so one way of stating it is energy lost or gained by the system equals energy gained or lost by the surroundings. This is one way of stating the first law of thermodynamics, is energy lost by the system is the same as energy gained by the surroundings. Another way of saying this is one way of saying it. Another way of saying it is you don't gain or lose, you can't create or destroy energy. Or destroy. Let's see, there's supposed to be OR. Or destroy energy. You just move it around. Just move it around. All right. So you can't create or destroy energy, you just move it around. Energy lost is the same as energy gained. There's another consequence of the first law of thermodynamics is the energy of the universe, everything is fixed. A lot of thermodynamics and various laws and equations don't work unless you actually assume that the entire universe has a fixed amount of energy and all you're just doing is just moving things around. So system you either lose energy or you gain energy, but you're not creating energy, you're not destroying energy, just moving it around. Things gain, things lose. You give, you take. That's the first law of thermodynamics, okay? All right, so the first thing that we're going to look at as far as delta H's or enthalpies is something called enthalpy of reaction, okay? So now we're going to get into the actual practical aspects of chemistry when we do reactions, and we're going to call this energy of reaction or enthalpies of reaction. All right, here we go. All right, now remember, if it is negative, if delta H is negative, this makes it exothermic. And if delta H is positive, this makes it endothermic. Okay? All right. Just a sign convention. Positive versus negative. And so let's say we have this reaction here. Let me take a reaction. And it doesn't matter. What I'm going to do is I'm just going to say, all right, let's go back to HCl plus sodium hydroxide gives me water plus sodium chloride. And this is an acid-base neutralization. This we've seen from the previous chapters. This is one of many reactions. And the part that I'm going to add to this is I'm going to put off to the side, and this is a hypothetical number, by the way. I just don't feel like looking it up. And it's delta H. Let's say, just for the sake of argument, let's say it was 88.0 kilojoules. Remember when I said that, usually you don't see joules very much. Usually you see kilojoules, which means 1,000 joules. And so for this particular reaction, what we're saying is the enthalpy of reaction is minus 88.0 kilojoules, which means that the reaction is exothermic. It has a negative sign. It makes it exothermic, which means this reaction releases heat, which means another way of looking at it from a subjective way is it will get hot. The reaction gets hot. Exothermic reactions get warmer or hotter as they occur. And so if we were to do this in water, for instance, it would actually heat up the water that it's in. Okay, so this is exothermic. Now, how do we end up using this sort of thing? Now, this delta H is now this is important, this is per 1 mole HCl, it's per 1 mole sodium hydroxide, it's per 1 water, and it's per 1 sodium chloride. Now, I picked a reaction that had 1:1 ratios all the way down, just to keep things simple for the first one. But you got to keep in mind that this whole thing, this entire thing here goes together. This whole equation with the delta H equals minus 88 kilojoules, it all goes together. It's very easy to look at this and say, okay, I have an equation that's balanced, and then to look at the delta H and say, well, that's something completely different. They go together. All right, they belong together. All right, now why is that important? Well, let me show you something here. Let's just do a problem here. So, how much heat in kilojoules from the reaction of, let's say, 14.2 grams sodium hydroxide with excess hydrochloric acid. Okay, how much heat in kilojoules from the reaction of 14.2 grams sodium hydroxide with excess hydrochloric acid? How much heat would you get? Okay, now, chapter 3, chapter 4, what did we do? We would take so many grams of something or so many milliliters of something, and you could tell me how many grams of stuff you're going to get. And you should be able to tell me, or how many milliliters it would take, or whatever, some sort of quantity. Now we're being asked how much heat in kilojoules. This is what we're being asked. Now I'm going to tell you, if you're up on chapter 3, chapter 4, this is not a stretch. You look at it and you say, well, you know what? Heat in kilojoules. Where do I see kilojoules? Where do I see heat? And the answer is right here. There's heat. You have kilojoules. All right. Well, we know that's going to play a part somewhere in our setup. This is going to play a part somewhere in the setup. Now, nothing's really much changed from what we did before. What do we see over here? I see grams, and I see grams sodium hydroxide. What do we know when we see grams of anything? We know that we need the molar mass of sodium hydroxide. So we say sodium hydroxide is what? The sodium part is 23.0. We have the oxygen part was 16.0. And the water, the hydrogen part, which is 1.0, and we say sodium hydroxide is what, 23, what is that? That's 40, is that 40? Yeah, that's 40. 40, add that up, make sure that's right. Yep, 40.0 grams sodium hydroxide for every mole. Sodium hydroxide. Nothing has changed here. I know we're on chapter 5, but really nothing's changed. This is why it's so incredibly important that you have chapter 3, chapter 4 down. Because once again, what are you looking for? Do I see grams? Do I not see grams? Yes, I see grams. I need the molar mass. All right. Do I see grams anywhere else? The answer is no. Do I see myself? Now, here's the important part. Here's a question that we asked ourselves from chapter 3, chapter 4. Am I going from one thing to something else? Remember when we said that in chapter 3, chapter 4? I said, if you're going from one thing to another thing, what do you need? You need something called the mole ratio. Anytime you're going from something to something, you need the mole ratio. And what did you need? You needed the balanced equation. What do we have up there? We have a balanced equation, except now I have energy with it as well. And what did I say? I circled the whole thing in blue and I said it all belongs together. And notice I said thing to thing. I never said atoms to atoms or molecules to molecules or molecules to atoms. I always said you got one thing going to another thing. It's not because I was being lazy with my English. I'm trying to be really general. You're going from one thing to another thing. What are we going between? We are going from kilojoules. You see that? We're going from kilojoules and grams sodium hydroxide, or just sodium hydroxide. We're going between these two things. What are we going, and what does that mean? That means we're going between the sodium hydroxide and the heat. We're going from sodium hydroxide to heat. This is one thing to another thing. And what did we do if we were going from, say, one molecule to one molecule, had mole ratio between the two? Now, this is not a mole ratio, but it's still a ratio, and we would say minus 88.0 kilojoules for what? Every 1 mole sodium hydroxide. Minus 88.0 kilojoules for every 1 mole sodium hydroxide. We have the kilojoules, and this kilojoules, this 88 kilojoules, is for the entire reaction. And it's for every 1 HCl, I get 88 kilojoules of energy. For every 1 sodium hydroxide, I get 88 kilojoules of energy. For every 1 water that I pick up, I get 88. And for every 1 sodium chloride that I form, I get minus 88 kilojoules of energy. It's one thing to something else, except now it's not a mole ratio between the two products, or the two reactants, or the reactant and the product, or whatever. It's between the energy and whatever it is that you're starting with. And so now we have a conversion factor. I have a way of going from mole sodium hydroxide to kilojoules, and from kilojoules to mole sodium hydroxide. And so now what do? I just draw a line, draw another line. That's what we're going to do. We're going to draw a line, draw another line, and we're going to just solve. So here we go. What do we always start with? We always start with what? The measured number. Always the measured number. Every equation that we'll ever do for this entire semester will start with whatever the measured number is. What's the measured number? Here is the measured number right here. There it is. It's the 14.2 grams sodium hydroxide. There it is. And so our measured number is 14.2 grams sodium hydroxide. You see, this answers the question that was never answered for me when I was in your position, which was, Where do you start? Well, you always start with the measured number. The measured number is 14.2 grams sodium hydroxide. Now what do I do? I look around and I try to find, if I can't remember that whenever you go from grams to something else, the next thing up is always the molar mass, but not remembering that, what do I look for? Right here. What do we have over here? We have, you see, the gram sodium hydroxide. So I have to flip this over. And so we're going to flip this over and it's going to become mole sodium hydroxide for every 40.0 grams sodium hydroxide. You see how this is working? It's working exactly the same way as what we did before. And so now I've used this, and I like to put a little check mark just to make sure I don't reuse these things. And now what? The only thing that's left that has moles sodium hydroxide is what? It's right over here. See, moles sodium hydroxide, which means the moles sodium hydroxide is going to have to go on the bottom. And so the minus 88.0 kilojoules for every 1 mole sodium hydroxide, and we're done. Check mark. There it is. Look, see? Gram sodium hydroxide, moles sodium hydroxide, moles sodium hydroxide. We canceled units all the way down. And now we pull out our calculator and I tell you how many kilojoules. And so we go 14, let's turn on my calculator, 14.2 times 88 divided by 40. And I get minus 31.2. Now don't forget the minus part, okay? Don't forget the minus part. Minus 31.2 kilojoules. Now, when I put this in my calculator, I often leave off the minus sign, and usually what I do is I fix the sign at the end. I just go ahead and put it back on. So when I put this in my calculator, I literally went 14.2 times 88 divided by 40, and then I put the minus sign back on. You can put the minus sign on in your calculator. It's just my personal bad habit, all right? But I do know I have a minus sign here. Everything else is positive, so our answer should be minus, and so that's minus 31.2 kilojoules from the reaction of 14.2 grams sodium hydroxide with excess hydrochloric acid. Okay, all right. So let's take a look at let's do another one. So how about let's have the combustion of methane. So let's take the combustion of methane. Methane is CH4. Combustion means it's going to be CH4 plus oxygen gas, and products of combustion are CO2 plus water. And let's say, and I don't know off the top of my head what it is, but I'm just going to give you an arbitrary number, okay? So don't go looking it up and saying, oh, Mr. Pierce, it wasn't this. I'm just giving you a number just so that we can do the math. And so let's say this was minus 890 kilojoules. And just for sig purposes, I'm going to put a decimal there to keep it as 3. Okay, let's say that delta H is minus 890 kilojoules. What does this make this reaction here? Does this make this exothermic or endothermic? What do you think? It's exothermic. Why is it exothermic? Because it has a negative sign on delta H. So this is exothermic, first off. This is an exothermic reaction. By the way, the combustion of methane, what is the combustion of methane? Combustion of methane is what happens in a Bunsen burner. Natural gas is mostly methane. And so when you burn it in a Bunsen burner, it produces a lot of heat, and well, that's what you have. You have an exothermic reaction. All right, so here's the problem. So let's let's say that we burn, let's say, how many kilojoules are released when, oh, I don't know, let's say 19.2 grams water is formed. Okay. How many kilojoules are released when 19.2 grams of water is formed from this reaction? Now, just like chapter 3, chapter 4, what do you have to have? You have to have a balanced equation. Now, since this is chapter 5 and we're dealing with heat, we do have the delta H, or the enthalpy of the reaction, is minus 890 kilojoules. All right? Okay. So what do we need to do? Well, first off, we go through the reaction, and anywhere where we see grams, I need a molar mass. And so the molar mass of water is 18.0 grams of water. Anywhere where you see grams, you need a molar mass. This is always going to be the case. Well, almost always the case. But it's certainly, you have this so many grams of it, and you're going to have to turn it into moles at some point. And so it's 18.0 grams of water for every mole of water. So I've got the molar mass of water. Do I see grams anywhere else? Why would you see grams somewhere else? Because maybe you're doing a limiting reacting problem. Limiting reactant problems, usually you have two things reacting together, right? You're trying to figure out how much you're going to get. And you have to figure out how much you're going to get. You're going to need to know both quantities. But this is not a limiting reactant problem. We have just the 1 grams, and we're assuming excess oxygen, and we got to figure out how much we've got. All right. And so are we going from one thing to another thing? And the answer is, and that should be how many, but how many kilojoules? We have kilojoules and we have water. We have two different things that we're going in between, aren't we? Kilojoules and water. And so what's the relationship between the two? Well, I know the kilojoules. What's the kilojoules? The kilojoules, well, we look up there and we see it's minus 890 dot for sig fig purposes, kilojoules. All right, but kilojoules per water, and we look over here and I see 2 waters for every 2 mole H2O. Remember, this minus 890 is for everything. It's for the entire balanced equation is minus 890. So it's for every 1 methane, it's for every 1 oxygen, it's for every 1 carbon dioxide, and it's for every two waters. And so if you have 2 up there, well, you've got minus 890 for every 2 moles H2O. So this 2 has to end up over here. All right. That's where we got the 2 from. I got it from the balanced equation. Okay. And so I look over here and I say, you know what? I don't see anywhere else where I have grams. I don't see that I've got more than one thing going on, which would be a limiting reactant problem. And I don't see anything about, your actual measured amount, which would be a percent yield or something like that. And so this is all I see. I see grams and I see the kilojoules for every 2 moles of water. And so now what? Well, I'm going to go ahead and just draw a line. Here we go. I just draw a line. Draw another line. What do we start with? We start with what? We start with the measured number, always. Whatever it happens to be, that's the measured number, is 19.2 grams of water. So we start with that. So we say 19.2 grams H2O. If you haven't figured it out by now, there's a reason why we label everything. And we label everything because we're going to have to cancel units no matter what we do. We're going to have to cancel units. And so I have the grams water. What has grams water in it? Well, that's the molar mass of water. So we say a mole of water is 18.0 grams of water. There it is. Boom, we used it. And the only thing that left that has moles water in it, and remember, this thing's got to get copied down the same way, and we say minus 890 dot kilojoules for every 2 moles water. That 2 has to make its way down, okay? Y'all, it has to make its way down. All right. If you're going to forget something, that's what you're going to forget. And so now we can put this in our calculator. And so let's see, we have 19.2 times 890 divided by parentheses 18 times 2, close parentheses, and that would be 474.6. So we got to go 3 sig figs. Remember, this is a minus here, so our answer should be minus as well. So we go minus 475 kilojoules. And there you go. That's our answer, is 475 kilojoules. So now, it is tempting to jump straight to the setup down at the bottom. It's tempting, but don't do it. If you treat everything just like we did chapter 3, if you treat everything just like we did chapter 4, then these things set themselves up. And so you always start with the measured number, and you start, what do? You cancel units as you go, and you can't help but get the right answer at the end. All right. So whatever you do, resist the urge and temptation to try to jump to the setup right away. Now, you may do these often enough to where you will say, I've got this, and that's great because I can do these things. Most of the time I can do it without thinking too much about, the setup. But most of the time when I'm doing these, I actually do go through the trouble, and I very carefully go through and pull things down. I've been doing this for a lot longer than you have, and I still pretty much do it the same way I'm showing you right here. I don't jump to the final setup. And the bottom line is there's just so many different ways of doing this, okay? And I'm showing you the basic steps, okay, for doing enthalpies of reaction, okay? All right, so this is a good stopping point. I'm gonna go ahead and stop recording. And let's see, stop there, stop